Over to you, Oscar.
Thank you for the introduction, and I want to thank the organizers for the opportunity of being here, giving this talk, which is a joint work with Ruth Bitt, Campamores Sturzberg, Francisco José Ranz, and Javier de Lucas. Well, so before starting, I just want to say that I think we all know what the idea of a mixed superposition rule is. For instance, let us consider this inhomogeneous linear system of ordinary differential equations. We all know that the general solution of this system can be expressed in terms of the general solution of the homogeneous system and one particular solution of the inhomogeneous system. So this is the idea of a mixed superposition rule. But before entering mixed superposition rules, I will talk about usual superposition rules. And this is known as a Lie system, as Thomas said yesterday. So before starting, this is the very well-known example of the Dirichlet equation, which is the following first-order differential equation on the real line, where B0, B1, and B2 are arbitrary time-dependent smooth functions. Although the expression of this ODE is quite simple, I mean, it is polynomial. In general, it cannot be solved by quadratures. But nevertheless, what we know is that if we had 4 different particular solutions, their cross radius is constant. Their cross radius is this expression here, right? And from this expression, we can express, for instance, x1 in terms of the other 3 particular solutions and our constant k. And the important thing is that this expression for S1 does not hold only for S1, but for the general solution of the Dirichlet equation, right? And this expression here allows us to express the general solution of the Dirichlet equation in terms of 3 particular solutions and 1 constant. And this is known as a superposition rule. So in order to define this in a more general geometric framework, let me introduce what a time-dependent vector field is, although Thomas already introduced it yesterday. A time-dependent vector field on a manifold M is just a smooth map X from R times M, where R refers to time, and M is our manifold to a tangent bundle of M, such that the following diagram commutes, right? Our equivalent state, X is a section of the pullback of the tangent bundle of M along the projection from R times M onto M. Or equivalent state, X is a T-parameterized family of usual vector field on M, right? Associated to this time-dependent vector field, we have the system of ordinary differential equation in no map form. And what is a superposition rule? Well, it's just a map phi from L copies, right, of M, and another extra copy of M onto M. The dash arrow here just means that this map is in general only locally defined, right? And such that the general or generic solution of our system X can be expressed in this form, right? In terms of L particular solutions, well, generic particular solutions, and a certain point K, which is related to the initial conditions of our system, right? So a natural question now is how to know when a system has or not a superposition rule. In order to introduce this, we deal with the so-called Lie systems, right? A Lie system on a manifold M is just a time-dependent vector field of our manifold, which is a curve taking values in a finite-dimensional Lie algebra vector fields V. And this V is a so-called Bessiot-Goulver Lie algebra associated with our system X. And the following theorem, which is due to Lie himself, states that X admits a superposition rule if and only if it is a Lie system. So back to our Dirichlet equation, we know that it admits a superposition rule, so let us see that it is a Lie system, right? The associated time-dependent vector field X is the following one. We have B0, B1, B2, and these 3 vector fields, which have the following commutation rules, and therefore they span a finite-dimensional Lie algebra, which is isomorphic to SH1. So it is a Lie system. Okay, so now let me introduce mixed superposition rules. The idea is just, in the definition of the superposition rule, to change the particular solutions and not to, I mean, they don't have to be particular solutions of the same system, right? That is the idea. So the question is, under which conditions the generic solution of a given system X on a manifold M can be expressed in terms of a generic family of particular solutions of possibly different systems from X1 to XL, defined on possibly different manifolds, from 1 to ML, and some constant related to the initial condition, right? So we define a mixed superposition rule for a system X on a manifold M in terms of some auxiliary systems as a locally defined map phi from the product of the auxiliary manifolds and our manifold M onto M, locally defined, so this is the dash arrow, through which we can express the generic solution in terms of blah, 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 as I said, right? And the question now for mixed superposition rule is how to know when a system does admit or not a mixed superposition rule. And we have a similar characterization as in the case of superposition rules, and is this theorem, which is due to Grabowski and De Lucas, and it states that X admits a mixed superposition rule if and only if it is allocistic. That is, a curve taking values in a finite dimensional algebra of vector fields. Right? Some examples of systems admitting mixed superposition rules in terms of other systems, right, different ones, are, for instance, inhomogeneous linear systems and the so-called Riccati hierarchy. Right? The Riccati hierarchy is a generalization to higher order differential equations of the usual Riccati equations. Right? And in this case, it is in terms of homogeneous linear ordinary differential equation. Okay, so the geometric sketch of how mixed superposition rules, it is the following picture, right? There is a one-to-one correspondence between mixed superposition rules in terms of some auxiliary systems and local inverses of this map, right? Which is PR1 hat and psi. And PR1 hat just denote the projection from the manifold, which is the product of M and all the copies of M1 to L, and to the product of M1 to ML. Yeah, this is just dropping M, right? And psi here is, if we want, trivializing submersion, right, for the foliation defined by these vector fields. And this product here for the vector fields is just the what is called the direct product, right? So we have the xt times x1 t times xl t. Right. This would be on a point x, x1, xl, right? T here is fixed, right? This is just taking the first one on the first point plus this one here on x1 plus dl here on the lth coordinate, right? Well, it's coordinate on the lth point, right? And this condition here for the submersion means that these vector fields are tangent to the foliation defined by psi. Right? So in order to construct mixed superposition rules, what we look for is for these trivializing submersions. Right? So somehow to first integrals of this vector field here. Right? Okay, and what we did in our work is at least to recognize or to find relevant families of systems of ordinary differential equations which do admit mixed superposition rules in somehow natural way. And we identified two different families. The first one is indeed very geometrical one, and is the so-called of primitive Bessiot-Gulverly algebras. A Bessiot-Gulverly algebra, right, which is just a finite dimensional algebra of vector fields, is said to be primitive if there exists a proper distribution, which is regular, I mean of constant rank, and integrable, that is involutive, such that V acts as least symmetries of this distribution, meaning that they preserve the space of sections, if you want, right? The bracket of B with every section of D stays again in D. And of course, assume the regularity condition that the Leaf space is a manifold, right? And the projection onto the Leaf space is a submersion. We have the following exact sequence of the algebras, right? Okay, so how to apply this framework of primitive Bessiot-Gulverly algebras to these systems? Let X, any Lie system such that V, this primitive Bessiot-Gulverly algebra, assuming this regularity condition, is a Bessiot-Gulverly algebra of X. And we have two cases. The first one is when V does not contain vector fields which are tangent to the foliation defined by D, right? In this case, the general solution of our system X is completely characterized in terms of particular solutions of the projective system, right? And, well, on the case that when V does contain vector fields which are tangent to the foliation, in order to construct the general solution of X, we need also particular solutions of X, and both of X and the projective system, right? So the best case is, for instance, the first one, right? And this is the first family, very geometrical, and we have also identified another family which is indeed very algebraic. And this is the one of semi-direct sums. So let now X be a Lie system which possesses a Bézier-Goldberg algebra, which is a semi-direct sum. V1 refers here to the subalgebra and V2 to the ideal, right? And we define the part of our Lie system X which takes values in the subalgebra V1 as the unique time-dependent vector field Y on M, such that for every t, yt stays in V1 and the difference of X and Y for every t stays in the ideal, right? We have proof here in this contest that in this case, right, for semi-direct sums, our Lie system X admits a mixed superposition rule depending on certain S particular solution of X and K particular solutions of Y, where Y is the part taking values in the subalgebra, and these X and K are some integers such that the so-called diagonal prolongations of the subalgebra V1 and V2 possess a modular basis, right? The diagonal prolongations is just taking the direct product of a vector field with itself, right? In this case of K, taking the direct product K times, and in the case of S, well, S times, right? A modular basis just means that these subalgebras, well, the algebras admit a basis of vector fields which are linearly independent over the space of smooth functions, right? Or in general over a generic subset, I mean open and dense, right? But one of the main features of Lie systems is that they can be made compatible with plenty of geometric structures. Most of them, K-contact, symplectic, Poisson, Jacobi, whatever you want. And using these compatible geometries, we can construct these superposition rules in a very efficient way. And in this work, we focus on how to apply these constructions to Dirac geometry, and and how to develop an algorithmic framework to construct mixed superposition rules. So just let me recall a few basics on Dirac geometry. So first of all, we will consider the generalized tangent bundle of our manifold M, which just is the Whitney sum of the tangent bundle of M and the cotangent bundle. And we keep this generalized tangent bundle with two structures. The first one is the D-symmetric pairing, right? And the second one is the so-called Hoffman bracket, right? Which is defined as follows. We take two sections of our generalized tangent bundle, a vector field X and one for alpha, vector field Y plus one for beta, and the Hoffman bracket is defined as the Lie bracket of X and Y, the Lie derivative of beta with respect to X minus the contraction of Y and the alpha. So what is then a Dirac manifold? A Dirac manifold is over M and L, where L is just a subbundle of the generalized tangent bundle, which satisfies two conditions. The first one is that L is Lagrangian with respect to a symmetric pairing, and the second one is that L is involutive with respect to the Hoffman bracket. Right? In some works, people just use the first condition. For instance, this is the case of Manolo's poster, and Dirac manifolds satisfying only the first condition are called almost Dirac. But I will need the second condition, right? Which is the one giving L indeed the structure of a Lie algebra. So examples of Dirac manifolds. Well, pick a two-form omega in our manifold M, pick a bivector pi on our manifold M, and through contraction, these omega and pi determine morphism of vector values. In the case of omega, from the tangent to the cotangent, and in the case of pi, from the cotangent to the tangent, right? And their graphs are indeed Dirac structures if and only if, for the case of the two-form, it is closed, meaning that it is presymplectic, and for the case of the bivector, if it is Poisson, meaning that it is Scouten-9 on its bracket with respect to itself. Okay, so some relations about, some geometric structures relative to standard inclusions. The intersections here, some of them for sure are non-trivial, are as follows, right? We know that every coorientable contact manifold is indeed presymplectic by taking the differential of the contact form, and we also know that every symplectic manifold is indeed presymplectic, right? And presymplectic manifolds are Dirac. We also know that coorientable contact manifolds are certain type of Jacobi manifolds, such that the associated Dirac vector field is nowhere vanishing. These are also Dirac, and Poisson manifolds are also Dirac. Right? So these are some relations, but I will focus on only on coorientable contact and presymplectic. So, how to analyze dynamic on Dirac manifolds in order to make Dirac geometry compatible with Lie systems? Well, we say that a smooth function on a Dirac manifold is L admissible for our Dirac structure L, provided that there exists a vector field of M, a so-called Hamiltonian vector field associated with F, which in general is non-unique, such that xf plus the differential of our function is a section of the Dirac structure. In this case, the space of admissible L functions is a Poisson algebra with the following Poisson bracket, right? And the Poisson bracket of f and g, where f and g are both L admissible functions, is defined as, well, pick any Hamiltonian function associated with the first one and take the derivative of the second function with respect to this vector field. And this does not depend on the choice of xf, right? One of the main properties of this space of L admissible functions is that if we have a finite family of L admissible functions, say f1 to fr, and we have a capital F, a smooth function from R to R, then the composition of this capital F with f1 to fr is again an admissible L function. And this is useful in order to prove the following property. Provided that we have an abstract, finite dimensional in general, Lie algebra G, and a morphism of Lie algebras from G onto the space of L admissible functions, we can define, as one expects, an associated moment map. This is a map which goes from our manifold M, where the Dirac structure is defined, onto the dual vector space of the Lie algebra, and is defined through contraction as follows, right? We pick a point X of our manifold M, pick a vector V on the Lie algebra, and then through contraction, the moment map is defined as, well, pick the element V of the Lie algebra, through the morphism phi, look to the L admissible function, which is phi V, and then evaluate this function at the point X of the manifold. Right? And this is a smooth map, and its pullback takes values in the space of L admissible functions, and this can be proved using the previous bullet. And moreover, with respect to the usual Poisson structure of the dual vector space of the Lie algebra, the Kirillov-Constant Poisson structure, this is a morphism of Lie algebras, right? Well, sorry, of Poisson algebras. And how to make Dirac geometry compatible with Lie systems? Well, it's very natural, I think. A Dirac Lie system is a triple, which is formed by a Dirac manifold and a Lie system which possess a Béziot-Goldberg Lie algebra, which is formed by Hamiltonian vector fields relative to the Dirac structure. In such case, we can prove that there exists a finite dimensional Lie algebra consisting of L admissible functions, such that our Béziot-Goldberg Lie algebra is formed by Hamiltonian vector fields associated with the functions of this finite dimensional Lie algebra of L admissible functions. And how to construct now constant of motion and therefore superposition rules? Well, we pick now an abstract Lie algebra with G, which is isomorphic to H, right? This is just picking a basis of H. And we have a morphism of Lie algebras from G onto the space of L admissible functions, such that its image is H, right? And in order to construct a constant of motion, what we do is we pick C, any Casimir function of the Poisson structure on the dual vector space of the Lie algebra. This is just a function which Poisson commutes with every smooth function on the dual vector space, and then is pulled back through the momentum map. It's a first integral of our second X. Right? And this is the method which one uses to construct a superposition rule. Indeed, we have developed a very general theory of how to construct these mixed superposition rules in a very algorithmic way, using well-behaved Poisson coalgebras. This requires using a bit of functional analysis and complete tensor products, but somehow I prefer to skip that formalism and give an example, right? And, well, using also moment maps, co-model Poisson algebras, coaction, and so on. A very algebraic theory, but, I mean, for me it's nice, but the details are a bit hard, so. Well, just let me give an example, which is a time-dependent thermodynamical system. Okay, we will consider the thermodynamical phase space, which will be R5, with the so-called Gibbs one form. On R5, this is a particular case on how the theory explained by Adam yesterday. We have two sets of variables. Extensive variables, which are U, S, and V. In this order, they correspond to internal energy, entropy, and volume. And we have also intensive variables, T and P, which refer to temperature and pressure. The Gibbs one form in these coordinates read as follows, right? And it satisfies this condition, meaning that it is, as we saw yesterday, a contact form. And we now consider the following Lie system, right, on this space. And it reads as follows in terms of 6 vector fields, which we will see in a few minutes, and 6 time-dependent smooth functions. Well, this system has somehow 2 different parts. The part which is relative to the extensive variables is linear and therefore quite trivial, because to obtain a general solution of a linear system, we just pick 3 particular solutions and a linear combination of them. But the part which is relative to the intensive variables, it is not that easy. It is a projective Riccati equation, and to obtain the general solution of this system is in general quite hard. But what we will show is that using indeed also the extensive system, we can provide a mixed superposition rule for this intensive system in terms of a Dirac structure somehow, right? So the procedure is done as follows. We have this following 6 vector fields of the above decomposition, and then span a Bessier-Bernoulli algebra, which is isomorphic to the semi-direct sum of SL2R and R3. This means that since we have a semi-direct sum, we can apply our algebraic theory, right? And now the question is how to derive a Dirac structure compatible with this system. Well, the procedure is indeed very geometrical. We pick the following subalgebra: V prime, which is spanned by S1, S3, S4, S5, and S6. And this is isomorphic to V2, a semi-direct sum with R3, where V2 is just the Borel subalgebra of S2. And these vector fields have the following wedge product, and this means that whenever the entropy and the so-called Gibbs free energy, which is that smooth function there, is non-vanishing, if we restrict our system to that open subset, then this is a so-called locally automorphic Bessier-Bernoulli algebra. And this means that when we look into the space of symmetries of this Bessier-Bernoulli algebra V prime, formed by those vector fields commuting with all the vector fields of V prime, that space is a finite dimensional algebra and isomorphic as well to V2 semi-direct sum with R3. We pick now a dual coframe of a basis of the space of symmetries, and is formed by these 5 one-forms. And of course, as one can expect, they satisfy the following molecular equations of this Lie algebra. And the striking point is that if we pick now any linear combination of these one-forms, it will be an invariant form for V prime, meaning that the Lie derivative of every element of V prime with respect to eta will be 0. In this case, if we pick this eta, it lies in the same conformal class of the Gibbs one form, and it is a contact form on M, right? Such that X is a Dirac system relative to the pre-symplectic form, right? And using the theory for Casimir functions and so on, we obtain the following mixed superposition rule for our intensive system, right? The projective Riccati equation, in terms of free constants, one particular solution of the extensive system, one particular solution of the extensive system with constant entropy. This, we obtain it using the reduction through an imprimitive Bessier-Bernoulli algebra, and one particular solution of the system associated with the Levy factor of this SL2 semi-direct sum with R3. This system, right? And finally, some conclusions will be to extend this to PDEs and so on, and well, in terms of some technical things. And finally, these are some references. So thank you for your attention.
Probably time for one big question. We have one.
Yeah.
Can you go back to the contact form divided by the...
Yeah.
Yes, this
Theta.
So if you think of this as so if you think about the induced Jacobi structure of this one form, does this coefficient, which might be 0, can become regular? So I don't know.
No idea.
Okay.
I don't know.
Okay.
And if I may ask a question, why have you chosen such a particular Lie system to analyze? Does it come from any natural?
No, we constructed this system using, first of all, representation of Lie algebras, and then scaling symmetries. It comes from an homogeneous symplectic system.
Okay.
Quite quickly, because this construction and this whole Dirac approach works in this case because we have it's not nice to work out because we have automorphic. The what happens if one is not automorphic?
To derive a compatible geometric structure. As you know, I mean, there is no general method to do that. In general, there is no general method.
Thank you, Oscar. Let's thank you.